Intermolecular Forces, Part 2, Section E. Chromatographic separation of compounds involves substances having different abilities to stick to a surface of a stationary phase. So these compounds have different intermolecular forces to this stationary surface, and a liquid washes these compounds off of the surface at different rates. That's what causes the separation. Silica gel is an example of one of these stationary phases. It's an adsorbent for compounds, and it has OH groups on its surface. These OH groups allow silica gel to both donate and accept hydrogen bonds, making it very sticky. If you look at compound A, it has an OH group as well, so it can both accept and donate hydrogen bonds to the surface of silica gel, and that allows it to bind pretty tightly. However, compound B can only accept hydrogen bonds from silica gel, so it doesn't stick quite as well. In essence, that means compound B should be washed off the silica gel more quickly than compound A, and we'll see that in our examples. Okay, here I'm going to illustrate chromatographic separation of compounds A and B via column chromatography. So a solvent is going to wash compounds A and B as a mixture down a column of silica gel, and that's going to cause separation because compound A sticks more tightly to the silica gel than compound B. Now, in this animation, I'm going to show bands for compounds A and B as being visible, but in reality, they wouldn't be to the naked eye. Thin layer chromatography, or TLC, works in the opposite direction of column chromatography. Now, instead of our compounds falling down the direction of gravity through silica gel and separating, we're going to actually have the solvent pull the compounds up silica gel using capillary action, but the separation principles are the same. Thus, we would expect compound A, which is stickier, to be lower than compound B, which is less sticky, which should get pulled up the plate faster. You say that the RF of A, which is the distance traveled by compound A, divided by the distance traveled by the solvent, is less than the RF of B, which is the distance traveled by B divided by the distance traveled by the solvent. A is stickier, more polar than B, therefore it has a smaller RF. Now you can watch this animation of compounds A and B as they migrate up the silica gel surface. Compound A, of course, will have a different stickiness than compound B, and that will be illustrated by the number of hydrogen bonds that they make to the surface of the silica gel. Practice problem 5. What is the RF order from lowest to highest of compounds A, B, and C? Explain, drawing predicted interactions with the silica gel surface as part of your explanation. So you want to think about whether or not compounds A, B, and C first have the intramolecular hydrogen bond. If they have that, you want to draw that first. Then you want to take the compound and try to interact it with a drawn structure for silica gel. And you want to be able to create hydrogen bonding to the silica gel. Either your substance can accept hydrogen bonds or donate hydrogen bonds, or both, to the silica gel surface. And of course, the stickier your substance is, the more hydrogen bonds it has with silica gel, the lower the RF will be.